Hello again. Welcome to Property Relationships Part 2. And whereas Part 1 was on a saturated vapor, saturated water, Part 2 is on superheated vapor. And so we want to know, well, how would we find the properties of water stick with atmospheric pressure for a bit, at atmospheric pressure, but no longer at 212? What if it was 300 degrees? What if I wanted to find the enthalpy, how much energy there is in water at atmospheric pressure and 300 Fahrenheit? Well, the good news is there's a table for that. It is table A4E, properties of superheated water vapor, superheated vapor. Now these tables come in little chunks, and each chunk is for a given pressure. So if we, and there are lots of pages. I think this goes all the way up to page 874. We start at page 869, so there are five pages. The pressure that we care about is 14.7. So 14.7 psi. Now they're nice enough to tell us, hey, the boiling point is 212. These two tables, 10 psi and 14.7 psi, share the same temperature column over here. So I go to 300 degrees, and I come all the way across to the enthalpy at 14.7, and I see that it would be 1239.9. So I'm going to just flip back. The enthalpy right here would be 1239.9 BTUs per pound mass. Well, what if I wanted to know at 400? Oh, lucky us. 400 is on the tables. Oh boy, look at that. When I wrote the 1239.9, that was for 400. I bet you caught that. 300 was 1192.6, and 400 was 1239.9. So we're just going to take that, send it up there to 400, and say that H here was 1192.6. It's as easy as that. Well, what if we wanted to find the enthalpy, but the temperature wasn't that easy? What if the temperature was 350 degrees? I'll let you ponder that for a second. I see some pretty smart students out there. I bet you're saying, well, it's probably halfway between 1192.6 and 1239.9. And you would be right. What if we wanted to find it at 310? Well, then it would be 10% of the way from 1192.6 to 1239.9, and so on. When you find 10% of the way, or 50% of the way, or 99% of the way, we call that interpolation. Interpolation. All right. Well, that's superheated vapor. That was pretty easy. Next step. What happens when we are at different pressures than atmospheric? Draw our temperature entropy diagram. Draw our vapor dome. Draw the pressure line for 14.7 psi. Now, what do we know about this point? We know its temperature, 212. Where would the pressure line be? for 40 psi. Well, I want you to press pause and look in your steam table and find what is the boiling point for 40 psi. So hopefully you went to the pressure table, table A3. I meant table A3, and I should be at table A3E. And if I go to 40 psi, I see that the boiling point, the boiling temperature, is 267.26. So if this is 212, 267. So that means that the pressure line for 40 psi is above the pressure line for 14.7 psi. And it turns out that that's true up and down the entire vapor dome. In fact, the vapor dome is really nothing more than a graph of all those constant pressure lines. I can go to 500 psi, and the boiling point there is 467 Fahrenheit. .500 psi. And if I keep going, I eventually get to 3,230 psi. 3,230 psi. And the pressure there, or the temperature there, is 705 Fahrenheit. That's as high as it goes. Above that point, water doesn't exist as a vapor anymore. It's more like a plasma type properties, and that's called the critical point. We can go all the way down to 0.1 psi. I guess our table goes to 0.4 psi. And at 0.4 psi, the boiling point is 72 degrees Fahrenheit. So let's talk about this for a minute. What's going on? Well, think of a pot of water on the stove. This water is being held in place by the air pressure. Now, the air pressure is how many pounds of force are coming down every square inch of that surface of water. Well, when it's 15 pounds, that's holding the molecules together so that they have to get moving so fast, get moving to the point where the temperature is 212, and then they can start breaking apart. The bonds can start breaking. Whereas, if I had even more pressure holding the bonds together, I would need even more speed and more temperature to break the bonds apart. But what if there was less pressure holding the bonds together? Way less. Well, then the molecules would be having to move way less before they could start breaking apart. I bet somewhere in 10th grade or 11th grade, I remember for me it was 11th grade chemistry, my teacher took a little jar of water and then he put a vacuum bell over it, and it was room temperature, so 70 degrees, and then he started taking air out of this vacuum bell, and pretty soon the number of molecules in there were so few that instead of the collisions applying a force of 15 pounds on every square inch, it was down here to 0.4, and we got to see water boil at room temperature. Well, that's all that's going on here. All right, how are we doing for time? 10 minutes right on the nose. Okay, and that's it for Property Relationships Part 2.